Welcome. Today, we'll explore the design of a real-time top K ranking system, a popular interview question at companies like Uber. This system is essential for scenarios where you need to track and display the top K entities, such as users, drivers, restaurants, or products, based on their scores, updating in real time as new data arrives. We'll break down the requirements, discuss data structures, handle concurrency, and ensure robustness. Let's start by understanding what a top K ranking system is and why it's so valuable in modern software engineering. The top K ranking system is widely used in leaderboards, recommendation engines, and dashboards. Imagine a ride-sharing app ranking drivers by rating, or an e-commerce platform showcasing top-selling products. The system must efficiently update scores, retrieve the top K entities instantly, and handle removals. These use cases demand both speed and accuracy, especially as data changes rapidly. Understanding these scenarios helps us appreciate the technical challenges and the need for a robust, scalable solution. Let's clarify the main requirements. The system must support three core operations: updating or inserting an entity's score, retrieving the top K entities ordered by score, and removing entities from the ranking. Each entity has a unique ID and a numeric score. Ties and scores should be handled deterministically, typically by sorting entity IDs in ascending order when scores are equal. These requirements ensure fairness and predictability in the ranking results. Interact with the system. We'll define three main APIs: update entity ID, new score, top KK, and remove entity ID. The update function adds a new entity or updates an existing one. The top K function returns the top K entities, sorted by score and then by entity ID. The remove function deletes an entity from the ranking. These APIs provide a clear and concise interface for clients to manage and query the ranking data. Selecting the right in-memory data structures is crucial for performance. A common approach is to use a HashMap for O1 lookups and a sorted structure like a TreeSet for maintaining order. The HashMap maps entity IDs to scores, enabling quick updates and removals. The TreeSet, ordered by score descending and entity ID ascending, allows efficient retrieval of the top K entities and maintains the correct ranking order at all times. The HashMap is a fundamental data structure in our design. It stores each entity's unique ID as the key and the corresponding score as the value. This allows for constant time access, making updates and removals extremely fast. Whenever an entity's score changes, we can quickly locate and modify its entry in the HashMap, ensuring the ranking stays up to date with minimal overhead. The TreeSet is used to maintain a sorted order of entities based on their scores. It automatically keeps entities sorted by score in descending order, and by entity ID in ascending order for tie breaking. This structure supports efficient insertion, deletion, and retrieval, which is essential for quickly finding the top K entities. The TreeSet complements the HashMap, ensuring both speed and correct ordering. When an entity's score is updated, we first check if it already exists in the system. If it does, we remove its old entry from the TreeSet, update the score in the HashMap, and then reinsert the updated entity into the TreeSet. If it's a new entity, we simply add it to both structures. This ensures that the TreeSet always reflects the latest scores and maintains the correct ranking. Removing an entity is straightforward. We locate the entity in the HashMap, remove it from both the HashMap and the TreeSet, and the ranking updates instantly. This dual removal ensures that the entity is no longer considered in any future top K queries, keeping the results accurate and up to date. To get the top K entities, we simply iterate through the TreeSet and collect the first K entries. Since the TreeSet is always sorted, this operation is efficient and guarantees that we return the highest scoring entities, with ties broken by entity ID. This approach provides both speed and correctness for real-time ranking queries. Handling ties is important for fairness and predictability. When two entities have the same score, we sort them by their entity IDs in ascending order. This deterministic approach ensures that the ranking is always consistent, even when scores are identical, and prevents ambiguity in the results. In real-world systems, multiple threads might update scores, remove entities, or query the top K rankings at the same time. Without proper handling, this can lead to inconsistent data or even crashes. Addressing concurrency is crucial for building a reliable, thread-safe ranking system that can handle high traffic and parallel operations. To manage concurrent access, we can use a read-write lock. This allows multiple threads to read the top K rankings simultaneously, but ensures that only one thread can update or remove entities at a time. By separating read and write operations, we maximize performance while maintaining data integrity and preventing race conditions. When multiple threads call update or remove, the right lock ensures that only one thread modifies the data structures at a time. This prevents conflicts and keeps the ranking accurate. Meanwhile, read operations for top K can proceed in parallel as long as no write is in progress. This balance is key to supporting high-throughput, real-time applications. Sometimes, the system needs to process large batches of score updates, which may contain malformed or invalid records. Efficient batch processing is essential for scalability. We must validate each record before processing and ensure that errors in one record don't affect the rest of the batch. To handle malformed records, we can use a dead letter queue. This means that any record that fails validation or processing is moved to a separate queue for further investigation, rather than blocking the entire batch. This approach increases reliability and ensures that good data is processed without interruption. Before updating scores in bulk, it's important to validate each record. This includes checking for missing fields, invalid IDs, or non-numeric scores. Only valid records should be processed, while invalid ones are logged or sent to the dead letter queue. This step ensures data quality and prevents errors from propagating. Testing is essential to ensure the system works as intended. We need to verify that updates, removals, and top K queries all produce correct results. This includes basic CRUD operations, tie-breaking logic, and handling of empty collections. Comprehensive testing helps catch bugs early and guarantees reliability. Edge cases can reveal hidden bugs. We should test scenarios like updating a non-existent entity, removing an entity not in the ranking, or requesting more entities than exist. These tests ensure the system handles unusual situations gracefully and remains robust under all conditions. Concurrency tests simulate multiple threads performing updates, removals, and queries at the same time. These tests help ensure that the locking mechanism works correctly and that the ranking remains consistent even under heavy parallel load. It's important to verify that no data races or deadlocks occur. An object-oriented approach organizes the system into classes, such as entity, ranking system, and possibly batch processor. Each class encapsulates its own data and behavior, making the code modular and easier to maintain. This design also supports future extensions, like adding new ranking criteria or integrating with other systems. The entity class represents each ranked item, storing its unique ID and score. It also implements comparison logic for sorting, using score as the primary key and entity ID as the secondary key. This ensures that entities are always ordered correctly in the ranking system. The ranking system class manages the HashMap and TreeSet, exposing the update, remove, and top K APIs. It also handles concurrency control and batch processing. By centralizing these responsibilities, the ranking system class keeps the implementation clean and focused. For large-scale updates, a batch processor class can be introduced. It validates records, processes updates in bulk, and manages the dead letter queue. This separation of concerns makes the system more maintainable and allows for specialized optimization of batch operations. As the number of entities grows, performance can degrade if the data structures aren't chosen wisely. Using a HashMap and TreeSet ensures that lookups, updates, and removals remain efficient even as the dataset scales. For extremely large datasets, consider sharding or partitioning the data across multiple machines. Fault tolerance is vital for any robust system. By isolating malformed records and using batch validation, the system can continue processing valid data even when some inputs fail. Logging errors and using a dead letter queue ensures that no data is lost and that issues can be addressed later. A well-designed API is easy to use and understand. By keeping the interface simple, just update, remove, and top K, developers can quickly integrate the ranking system into their applications. Clear documentation and predictable behavior further enhance usability. To optimize performance, minimize locking duration during updates and removals. Use efficient data structures and avoid unnecessary computations. For read-heavy workloads, consider caching the top K results and invalidating the cache only when updates occur. Efficient memory usage is important, especially for large-scale systems. Regularly remove inactive or obsolete entities to free up space. Monitor memory consumption and tune data structures as needed to balance speed and resource usage. The system can be extended to support additional features, such as filtering by category, time window, or custom ranking criteria. By designing with extensibility in mind, you can adapt the system to new requirements without major rewrites. A real-time ranking system often needs to integrate with other services, such as databases, analytics platforms, or notification systems. Design APIs and data flows to support seamless integration, ensuring that updates and queries can be easily shared across the organization. Monitoring is essential for maintaining system health. Track metrics such as update latency, query response time, and error rates. Set up alerts for unusual activity or performance degradation so issues can be addressed proactively. Comprehensive logging helps with debugging and auditing. Log all updates, removals, and queries, along with timestamps and user information. This provides a clear history of changes and supports compliance and troubleshooting. Security is important, especially for systems handling sensitive data. Implement access controls to restrict who can update or query the rankings. Validate all inputs to prevent injection attacks or data corruption. Regularly review and update security policies. Robust error handling ensures the system remains stable under all conditions. Catch and log exceptions during updates, removals, and queries. Provide clear error messages to clients and ensure that failures in one part of the system don't cascade to others. Good documentation is key for adoption and maintenance. Provide clear guides on how to use the APIs, expected behaviors, and troubleshooting tips. Offer support channels for users to ask questions or report issues. Top K ranking systems are used in many real-world applications, from gaming leaderboards to search engines and recommendation systems. Their ability to provide instant, accurate rankings makes them invaluable for user engagement and business insights. If you're preparing for a software engineering interview, practice designing systems like the real-time Top K ranking. Focus on explaining your data structure choices, handling concurrency, and writing comprehensive tests. Clear communication and structured thinking are just as important as technical knowledge. Watch out for common mistakes, such as ignoring concurrency, not handling ties deterministically, or using inefficient data structures. Always consider edge cases and scalability from the start. These details can make or break your system in both interviews and real-world deployments. To recap, a real-time Top K ranking system requires efficient data structures, clear APIs, robust concurrency handling, and thorough testing. By following best practices and anticipating challenges, you can design a system that's both performant and reliable. For more on this topic, explore resources on in-memory data structures, concurrency patterns, and distributed systems. Practicing with real interview questions and building prototypes will deepen your understanding and prepare you for technical interviews. The best way to master system design is through practice. Try implementing a Top K ranking system yourself, experiment with different data structures, and simulate concurrent access. Each iteration will improve your skills and confidence. A well-designed ranking system can have a huge impact on user experience and business outcomes. Fast, accurate rankings keep users engaged and provide valuable insights for decision-making. Investing in robust design pays off in the long run. Designing a real-time Top K ranking system is a great exercise in balancing performance, correctness, and scalability. Whether you're preparing for an interview or building production systems, these principles will serve you well. Thanks for joining this deep dive into system design. Ready to take your skills further? Try designing variations of the Top K system, such as supporting time-based rankings or distributed deployments. Keep learning, keep building, and you'll be ready for any system design challenge that comes your way.